Dear ladies and gentlemen, dear colleagues, it's my pleasure and privilege to introduce you IFAR, International Forum of Aviation Research, the world's only aeronautical research establishment network. We started IFAR in 2010 and now have been growing, assembling 26 national research centers in total with approximately 34,000 researchers. Only one establishment per nation can join IFAR, and as you can see, we probably represent something like 90% of the major aeronautical research institutions around the world. IFAR aims to connect research establishments worldwide to enable information exchange and communication on aviation research activities and to develop among its members a shared understanding on challenges faced by the global aviation research community. IFAR's main goal can be shortly described as the information exchange, where we identify global priority research challenges for common action, networking with our yearly high-level summit, we connect all the principles, cooperation in order to stimulate innovation and improve our research achievements through collaborative activities, education, where we foster the next generation of global aeronautics engineers and scientists, communication, including to inform aviation related policies based on solid research and common IFAR decisions. The focus of IFAR is on non-competitive aviation research and development related to global technical challenges such as those pertaining to emission, noise, safety and security, efficiency, and steps to reduce the impact of aviation on climate and environment. Ladies and gentlemen, in today's IFAR lecture, we will discuss some existing challenges and provide you with our common view on how we could possibly address these challenges and contribute to accelerate innovations and to the benefit of society and industry. This might be now a good starting point for our discussion. Thank you for your attention and being with us.
Thank you very much and welcome to the IFAR ICAS lecture 2020, which is the ICAS conference general lecture number 5. The title is IFAR's Perspective on Sustainable Aviation. And the question is, can we achieve zero emission aviation and how can we achieve zero emission aviation? My name is Rolf Henke. I'm talking on behalf of the German Aerospace Center, DLR, and I will come to the other authors in a minute. About a year ago, 30 members of IFAR published a paper on zero emission aviation. In Germany, where I come from, we have a paper on zero emission aviation from the DLR and the German Industry Association, BDLI. We have a couple of thoughts on sustainable aviation fuels. We have thoughts on Fly Zero from the UK Aerospace Technology Institute. And we have even concrete aircraft by Airbus talking Zero E. So these are 3 types of aircraft flying with hydrogen. So a big topic, time to think about it, time to discuss it, which is the title of this IFAR ICAS lecture. This lecture is organized in 6 chapters. After my short introduction, Sergey Chernyshev, our present chairman of IFAR and the chief scientist of the Russian Sergey, will address the translation of zero emission into top-level aircraft requirements, TILA. I will talk a little bit about the propulsion system and energy storage afterwards. Then Xiasheng, the head of the Chinese Aerospace Research Establishment, CAE, will address the airframe systems. Michel, CEO of the Dutch Aerospace Establishment, NLR, will address zero emission operation, so it's airlines, ATM and airports. Then Bob Pearce from NASA will talk about stakeholder contributions, research, academia, industry, society and politics. And finally, Ibrahim Yimer, the head of aeronautics at the Canadian NRC, will address a roadmap to zero emission and give a conclusion. Finally, Michel will summarize and organize the question and answer session. So without further ado, I hand over to Sergey Chernyshev to the first chapter, talking of translation from zero emission into TILA. Sergey, please.
Thank you, Rolf. Nowadays, the problem of global aviation impact on environment is considered as a most critical issue. Science all over the world combine their efforts to find the most effective solution for the various industries to move forward to green environment-friendly technologies. As a key target, global society has defined the year 2050 as a carbon neutral or even zero emission point on a time scale. You can see in the picture the input of emissions from different economy sectors. All of them have to diminish their carbon footprint by 50% in average by the period less than a decade. As aeronautics research establishments, we are focused on aviation transportation emission reduction. In spite of the small relative share of total transport emissions, aviation has a dramatic impact on global warming effect due to carbon accumulation in the upper atmosphere, remaining there for decades. That is why emission reduction technologies for air transport system is so crucial in addressing climate change. The new technology solutions such as electric or hybrid propulsion, use of cryogenic liquid hydrogen, and increased aircraft energy efficiency will help in air transportation decarbonization. An application of the cryogenic fuel is considered as a revolutionary step for the future of aviation. To make these steps, various IFAR research establishments and Global Aviation Organization develop their respective strategies and technology roadmaps. They introduce slightly different approaches, but more or less they come to the same strategic solution, considering liquid hydrogen as a fuel of the future. In the Russian Federation, the hydrogen initiative for the national economy has been approved on the government level. The group of several IFAR members has recently developed its own view on zero-emission aviation. We call it Yimer. Yimer group is aimed for the development of aviation which is free of negative impact on planet, meaning close to zero emission, for their entire product life cycle. Yimer declaration was introduced to the world aviation community and public at the Berlin Aviation Summit in November 2020. It could be found in public domain. By considering the various innovative solutions, it is required to define the profile of the future aviation transport. The task for the nearest decade is to implement upcoming technologies in future aircraft and to provide the technology basis for the next generation of aviation. By solving the problem of clean air transport, the focus was made for the class of aircraft that have the most severe emission share of CO2. Considering technologies available now and in the nearest future, the reasonable concepts come to mind. Application of electric and hybrid electric power as a propulsion for the regional and short-range aircraft applied on the typical routes connecting European countries, American states, distant state regions, etc. Application of the hydrogen fuel for the mid-range aircraft with amount of passenger approximately 150 seats or more. The future concept should be proposed using real market parameters that would define so-called top-level aircraft requirements, such as fuel type, typical range, design cruise, emission level, noise level, operation costs, service goal, airport class. Based on these numbers, the proper selection of the technologies and their integration should be performed. Of course, the influence of other factors should be kept in mind. When we talk about application of new fuel, it is obvious to consider the corresponding infrastructure development and operation. Currently, Russia is participating in 2 European projects that cover the technology research on mentioned aircraft types. The first one is Footprint 50 that should provide the technology basis and system integration for the 50-seat regional aircraft. The second one is aimed for technological solutions for more than 100-seat passenger aircraft. Projects should give the answer to the critical technologies implementation to provide effective operational level of electric hybrid, electric power generation, power control systems, energy storage, overall system integration, operation issues. As was mentioned before, the development of infrastructure is an integral part of the transportation system. Here in the slide you can see some examples of the strategies for the production of hydrogen. Various ways to provide future consumers are considered by H2 pump storage, network distribution, gas storage, and liquid H2 local production, etc. And returning back to TLRs, for the regional aircraft, different concepts have been analyzed. TLRs should be implemented in the best way by considering available and upcoming technological solutions. Understanding of technological gaps helps to specify the topics of new studies and research programs. As example, here in the table you can see the parameters of the regional aircraft required for the Russian market. To cover the technological gaps defined along with key technology development, the conceptual studies should specify parameters of aircraft systems for the future development. Shown in the slide is this example of regional aircraft with a hybrid electric engine. Currently, there is a set of research projects in Russia aimed at technology development for hybrid electric aircraft with application of technology of high temperature superconductivity. The concept aircraft is under development stage right now. At this stage, the flight technology demonstrator was developed and assembled by the Russian project consortium, leading by the Central Institute of Aviation Motors, CIAM. This project has passed several successful stages, and target parameters have been reached both in the ground tests and in flight experiment. Technology demonstrator of hybrid electric propulsion installed on the Yakovlev Yak-40 aircraft, jet engine aircraft, flew in July this year at the International Moscow Air Show MAX 2021. It uses electric engine superconductivity electrical system that was placed in the nose of fuselage. Top-level requirements for large aircraft bring new challenges. Entire new approaches for aircraft design must be developed. Hydrogen as a fuel will radically change the aircraft configuration and structure for middle and long-range aircraft. New airport infrastructure also must be under consideration for the new type of aircraft. New regulations and certifications issues should come with that in global scale. So this slide ends my part of presentation. Thank you for your attention.
Let's come to the second part of this lecture now on the propulsion system and the energy storage. My name is Rolf Henke. I'm talking on behalf of the German Aerospace Center DLR. Content-wise, I will address the sustainable aviation technologies and challenges, take a closer look on sustainable aviation fuels and hydrogen, look at the aviation impact and technology assessment, and go for an outlook. These are the elements, the pieces of the puzzle we have available to shape the future of aviation. If I go in clockwise direction from the 3 o'clock position, batteries. We have new battery generations every couple of years. We have fuel cells. We can burn hydrogen directly in gas turbines. We may go for alternative fuels, sustainable aviation fuels. We may need new configuration, I will come to that in a minute, of the aircraft, new architectures of the aircraft and the aviation system as such. And finally go for new air traffic management, for example, on climate optimized altitudes and routes. Every one of these different elements may need technical solutions, may need certification, may ask for infrastructure on board or on ground, asks for different airspace, different air traffic management, and needs validated tools for design as well as for certification. And here you see the research effort needed for all these elements, and it is huge. We are not by far where we need to be to have really zero emission aviation. In addition, we need the links to atmosphere research, environmental chemistry, radiation medicine, research on acceptance, noise, technology assessment. So there's really much to be done. Overall, we have a couple of topics to be tackled in parallel. It's the energy source, it's the propulsion system, but then also the system architecture, the aircraft configuration. All this will be very expensive, so we need enabling technologies for a better efficiency of the aircraft, which is aerodynamics, lightweight, materials, automation, new ways of flying, so air traffic management. And finally, of course, we need new production systems and maintenance, repair and overhaul, so the whole life cycle. The propulsion system, the energy storage, and the IFAR configuration, all these are strongly coupled, linked by this, what I call the enabling technologies. What do I mean with this? If we go for electric flight, the first ideas we had about a decade ago were really on noise. And if we now have a look at the aircraft noise, these are the different elements. You see approach noise and the takeoff noise, the parts coming from the engine and the airframe noise. All this adding up, of course, on a logarithm scale, it's not linear. If we now change only the motor, so we still have the fan producing the thrust, but we change the motor from a gas turbine to an electromotor. Then we will still have a couple of noise sources, they will remain. So the fan is still running and producing the thrust. Of course, we get rid of the combustion, the airframe will still be the same. So without any change in aircraft configuration and the propulsion system, the major noise sources will remain. So a pure substitution will not lead to a noise reduction, even though we change the propulsion and the energy storage. This means, as I said before, if we go for the propulsion system and the energy, we need to tackle also the aircraft architecture and the way how to fly this aircraft. Let's take a closer look now on sustainable aviation fuels, SAF. There are a couple of studies around these days. I just picked two of them, one from Roland Berger, another one from RBP on the production of SAF. If we take a more global view on the four different energy sources, battery, fuel cell, direct burn of hydrogen and SAF, you can see the changes in CO2 impact on the aircraft design, whether we need large changes or not, the same on airport infrastructure, and finally on cost. The two arrows on SAF mean that on the one hand side, of course, we still have CO2 impact if we burn SAF, that would be the horizontal arrow, but due to the production and the overall balance, it's CO2 and climate neutral, that's the arrow going down. So it's in this case SAF, it's both. Interesting enough, now you can take a decision whether you bet on hydrogen or you bet on, what says Boeing, on pragmatism. Regardless which company is betting on what, this picture just shows that you have to take a decision on one way or another, and it will be very interesting in view of the next generation aircraft. Overall, SAF technology is known in principle, but mass production will need at least some 5 more years. SAF still means burning hydrocarbon-based fuel, so we will have CO2, NOx, water, soot, unburned hydrocarbons. However, SAF will be the first major step, a bridge to zero-emission aviation. But we have not reached it yet, and it is of unknown length. Now let's have a look on liquid hydrogen, LH2. Will this be the salvation of all the aviation problems? What do we need? Worldwide, somewhere, renewable energy to produce hydrogen, store it and transport it to one of the more than 600 large airports worldwide. Again, it needs to be stored there. We need then the fueling vehicles and the tanking process. Aircraft-wise, on the 20,000 large aircraft, we need the tanks, we need the architecture and the engines optimized for the application of hydrogen. And the question is, why do we do all this? Of course, it's on the emission. So the aviation emissions in case of burning hydrogen will be combustion products like NOx, limited, but still there will be NOx. Maybe CO2 depending on the process. There will be contrails and there will be contrail zeros. And both may cause problems, which we'll see in a minute. So we don't have a complete idea on the impact, but we know that we have to change the complete system, not only the aircraft, but the complete system of aviation in terms of application of liquid hydrogen. Hydrogen applications by no means are new. Aviation even started by hydrogen on balloons and zeppelins. Recently, there are many international papers being published showing an increased interest, if not expectation, for hydrogen. And the question is, are we on the hype curve again, as we have been in the 1990s? Meaning that we sort of inflate the expectations until we reach a peak, then we have to go through a valley of disillusionment until we reach a plateau of productivity. My impression is that is the case, that we are still not there yet, and that we sort of start to overload hydrogen. You have to take care and look what's the impact, what's the effort, and find clever solutions. One of the questions is where to position the tanks, the H2 tanks. This is the only example of a transport aircraft ever flown with hydrogen. It's a Tupolev 155, derived from a 154, and out of that test they designed in Tupolev 156, which unfortunately has never been built, but at least there was a concept based on flight test. There are a couple of concepts from Europe, from Airbus, Cryoplane. In my introduction I showed a couple of new aircraft from Airbus which will be hydrogen driven. There are concepts from research. Universal Hydrogen is a company in the US. We have concept, of course, from DLR. There's a NASA DLR design challenge, and this is a concept from the University of Stuttgart on an H2 driven aircraft and how to position and where to position the tanks. It's still a major question, the tanks. It's not solved yet in terms of TRL. We are somewhere at TRL 1 or 2, technology readiness level. So not really there concerning a product or even an entry into. Now let's come to the aviation impact to the climate. This is a very famous diagram showing all the elements contributing to this impact. It's measured in radiative forcing, milliwatt per square meter. On the right hand side it's warming, it's red, and on the left hand side the blue one is cooling. You see the different elements, CO2, NOx, water vapor, etc. Overall the CO2 is just 1/3 of the aviation impact. Non-CO2 elements sum up to 2/3 of the aviation impact in total. If we now go for H2 to hydrogen application, you see that we still have many of these elements like NOx, because it's a combustion process, water vapor, the contrails, the cirrus. So all this will remain, and water vapor is the strongest climate gas we know. So if we go for sustainable aviation fuels, we have all these elements. They may be then balanced by the production process on ground. If we go for fuel cells, we still have the water contribution, contrails, water and cirrus. And if we go for the direct burn, we have all this from fuel cells plus the NOx and eventually CO2 depending on the process. So just going for hydrogen or fuel cells doesn't mean that we don't have emissions at all. So we're going for zero emission aviation is a complete philosophy, not asking only for an energy source and propulsion, but for the whole system. The question to society and politics will then be, what is the requirement? Do we go for CO2? That we can do, I wouldn't say easily, but we can do it. Is it on climate? Is it on emissions? And this needs to be discussed and decided before we go for the next generation of aircraft. So this last foil then looks for the future of aviation and the future of aircraft propulsion, the title of my small part of the presentation. Today we have regional aircraft, helicopters, transport aircraft, etc., all with gas turbines and all running based on kerosene, Jet A1. In the future this may look like this, so it's really with different sizes of aircraft, commuter, regional, medium and long range. There will maybe different solutions, batteries, fuel cells, sustainable aviation fuels, hydrogen. The future will be manifold, which is good news for aircraft designer. There may be different solutions for zero emission depending on the category, and there will be a development from the smaller aircraft to the big ones. So in the last 3 decades we had a pure growth of the aviation system, 5% per year, which was always good news. The next 3 decades we have really to look for a transformation of the aviation system to go for something which the European Commission calls the Green Deal, zero emission aviation. Thank you very much. I now hand over to the lecture part number 3, the airframe and the systems by Xiasheng from CAE.
Thank you, Professor Henke. I'm Xiasheng, the chairman of Science and Technology Board of Chinese Aeronautical Establishment, CAE. It's an honor for me to share the overview of the development in airframe and systems of sustainable aviation in China. My lecture will be given in 3 parts. First, about CAE white paper. Second, brief the best practice in China. Last, but not the least, the approach to establish an ecosystem of development. The national development concepts for China are innovation, coordination, green development, opening up, and sharing. In 2020, Chinese government announced China aims to have CO2 emissions peak before 2030 and achieve carbon neutrality before 2060. The time is pressing, and to seize the opportunity, China must face the challenge at the same time. CAE has been working on sustainable aviation for years, and amongst those is a CAE white paper on development of electric aircraft released in 2019. The white paper suggests that China should give a priority to development of electric aircraft, varying from large sport to region and mainline aircraft. Focus on the development of key technologies such as overall design, high efficiency, and high power-to-weight ratio electrical propulsion, integrated energy management, as well as energy system. For electric light sport aircraft, the priority will be given to the all-electric propelled fixed-wing Jiren aircraft at Xiasheng by Liaoning Jiren Aviation Academy is the most successful product line in China. The Pioneer RX-1E is the first electric aircraft that complete certification in the world. Xiasheng 1EA extends the first duration to 2.5 hours with maximum takeoff weight of 630 kilograms. Now, the Academy is working on Xiasheng 4E. The 4-seat has made its maiden flight in October 2019 and aim to get TC in the first half of next year. The performance requirement of electric aircraft is mainly on range and flight duration, which are both limited by the energy density of linear batteries. To achieve better performance and practical ability, 4 highs should be reached, which are high aerodynamical efficiency, high efficiency of electrical propulsion systems, high battery energy density, and high structure efficiency. By achieving these factors, Xiasheng made a success. For the urban air mobility, priority will be given to eVTOL aircraft. One example in China is Yihang Company. It is focused on autonomous aerial vehicle AAV technology platform. Its AAV and conversion solutions cover the need for passenger and logistic air mobility, smarter city management, and area media solutions. The products type of Yihang AAV include single seat, double seat, firefighting, logistics, and the AAV operating platform involves operating system, command and control, vertiports, and charging systems. For commuters, priority will be given to all own hybrid electric commuter aircraft. CAE proposed a distributed electric propulsion layout, which uses the configuration to solve the range limitation caused by lower battery energy density. With this approach, 40 to 50% cruiser efficiency improvement can be achieved on commuter aircraft and more than 20% on regional aircraft, which can make greater contribution to practicability of all own hybrid electric aircraft. Another major research team in China is the key laboratory of aircraft electric propulsion technology at Northwest Portugal University, supported by Ministry of Industry and Information Technology. The lab has developed a distributed electric propulsion demonstrator. Apart from above, China has been many startups working in batteries, machines, and airframe. I have listed a few on the slides. Companies like CATL and MGL has made the greatest progress. In the interest of time, I'm not going to elaborate on all of them, why their contribution should not be ignored. For the research of key technologies for electrical region on mainline aircraft, there are some projects in planning recently. For the better development of electric aircraft, it's important that we establish an sustainable ecosystem that put every player in their best position. From my point of view, it should be built in 3 tiers. Tier 1, the OEM, like Comaco, work on the whole picture to conduct research on small electric aircraft, as well as mainline and regional aircraft by benchmarking its traditional models. Tier 2, SME and startup companies like Liaoning Ruixiang and Yihang attach importance to products, pursue short-term market returns, and focus on larger sport aircraft and UAV that have relatively high technical readiness level. Tier 3, the research community like IFAR members aim at next-generation aircraft to carry out key technologies research as system-level demonstration and verification studies supported by government projects. Now, I would like to give the floor to our next speaker, Mr. Pearce, for the fourth part of our lecture. In closing, I would like to extend my appreciation again to IFAR and ICAS for inviting me.
Well, thank you very much, Rolf, Sergey, and Sun, my IFAR colleagues, for having me here and being part of this lecture series, this IFAR-ICAS lecture series on sustainable aviation. My part of this lecture series will be around airlines, ATM and airports, as you can see in this opening slide. Let's start with some practical examples. What you see here is a picture of one of our research aircraft. It's a fully electric, so truly zero emission aircraft. It's a small aircraft, a two-seater with a limited endurance. And what happened a couple of weeks ago, it was the first landing of a truly zero emission aircraft on a large international hub, Schiphol Airport. And you see a lot of smiling people here, but on the far left, as you can see, that guy is a guy called Dick Benschop, and he is the CEO of the Royal Schiphol Group. That aircraft, our research aircraft, the Pipistrel, made a tour around the Netherlands. Now, the Netherlands is not the largest country in the world, as you can see, but we have quite a number of airports, smaller and larger, national and international airports. And the idea, the reason, the goal of that tour was first to gain some operational knowledge and experience with operating a fully electric aircraft, but also to demonstrate that sustainable aviation is possible. It's here, it's not going back, it's here to stay. And it's true, it's small, so the aircraft are small, the endurance is not that large, but it's here to stay. And one of the goals of NLR, together with the national colleagues and the international colleagues, is of course to improve the range of that aircraft to more operational, usable parameters. Well, some words about that aircraft itself. We learned a couple of things, of course. We already knew that the range, the endurance, is very limited. You have 30 minutes, and then you have an additional 30 minutes of reserve. On that aircraft, in the airport itself, you need, of course, a charging infrastructure. And that's not so severe, of course, for these smaller aircraft, but what you can easily imagine when the electric aircraft is becoming larger and larger, you really need to change the grid, the infrastructure in that case. You have to pay attention to the charging conditions, the correct temperatures. No unattended charging is yet possible due to safety requirements. Fire department has to be instructed, and how strange it may seem, in the beginning, when we just had that aircraft, it was really difficult to find the insurance, and the latter, by the way, is solved by now. So what does that mean? Because we all understand that such a small aircraft, only a two-seater, 30 minutes endurance, less the reserve, of course, is not so much of operational use. But just to mention, it's now beginning widely used, at least in the Netherlands, but what I understand also outside in Europe, for initial pilot training. For initial pilot training, of course, such an aircraft is very well suited. But we all know that there are a lot of activities throughout the world, smaller companies, larger companies, with the next generation of electric or sustainable aircraft. And what you can see most is that they are talking about 9 to 19 passenger aircraft with a range, I would say, up to 500 kilometers and perhaps even a little bit more. That is, from an operational point of view, still a limitation, but also an opportunity. If you look at the Netherlands, within that 500 kilometers, you can find major European cities like London, Paris, and Berlin. So that could certainly be a possibility for a new business model. Because nowadays when you want to fly, then you normally travel to a larger hub, and from that hub you fly to where you want to go. And if it's a longer flight, then sometimes before reaching your destination you have to change planes. Now, if we have smaller planes with a limited range, then more point-to-point trips are possible, I think. And that means basically, that means something for the larger international hubs, the larger hubs, but it also creates a new business opportunity. And from a passenger point of view, and I'm quite sure that everybody travels a lot in the audience of ICAS, that means everybody, basically every traveler wants to travel point to point, that you directly, in one direct flight, you reach your destination. So with those smaller zero emission aircraft or sustainable aircraft or climate neutrality aircraft, new business models are possible, and also low density routes can be created and are commercially viable. That means regional air mobility, and that means a chance for an improved and increased chance for regional airports. But it means something also not only for the aircraft, of course, but also for the airports. I mentioned that a little bit in my previous slides. The airport itself also wants to become zero emission, or at least climate neutral. So they are experimenting, that's happening in the Netherlands, but also outside of the Netherlands, I'm sure, with electric pushback for the larger aircraft, electric taxi. It also means something, of course, for the ground support equipment. When you have aircraft which have as an energy carrier or batteries or hydrogen, you need a refilling infrastructure in that sense. When you have electric aircraft, and especially when they are becoming a bit larger as our Pipistrel, then it means that you really need some grid adaptation for the electricity, and a lot of power, electrical power, has to be transported. But also the filling of hydrogen is of big importance, and hydrogen can be a little bit dangerous, and that means that you have to adapt the procedures. But again, like I said, new low-density routes are becoming then more and more commercially viable, and those are chances for the regional airports. With respect to ATM, air traffic management, things change because you have a more differentiation in aircraft types. Slower aircraft, faster aircraft, flying higher and lower, and more aircraft in the air. And that means that the separation of airports can become more and more stringent. Also, excuse me. Also, the noise footprint remains of importance. We did some measurements about the electric aircraft. And even an electric aircraft, a fully electric aircraft, makes some noise. It's less, certainly it's less, but it's not zero. And zero noise emission, I think that is virtually impossible. Every object that flies through the atmosphere makes some noise. But you have to do something about it to minimize it. So, to conclude this part of this lecture series, sustainable aviation is a necessity. Everybody agrees on that, there is no debate about it. But it can also be concluded that the technical challenges are very large. It's not an easy jump, but it can be done. The other side of the coin, I can say, it also gives new mobility opportunities. So I'm very, very confident that this road towards sustainable aviation is a viable road, and it will be a full reality not only for this small aircraft, but also the larger aircraft. Thank you very much.
Greetings from the United States. I hope everyone is doing well. I'm happy to be here today with my colleagues from the International Forum for Aviation Research to talk about perspectives on sustainable aviation. First, from a societal perspective, I think it's important to understand that the application of our research needs to deliver public benefit. And I think today those public benefits need to be in the form of greater system sustainability, greater mobility, in order to give citizens across the globe greater access to resources and opportunity, and certainly economic growth, again, for all citizens across the globe. NASA has a perspective around 4 transformations that will do just that. First, in the upper left-hand corner is the ultra-efficient transport. Today, subsonic transports are the backbone of our aviation system, will continue to be so for the foreseeable future. And so we need to make them as efficient as possible. We need to enable them to utilize 100% sustainable aviation fuels, and we need to make sure that they operate as efficiently as possible. In the lower left, ultimately we see the need to increase the speed by going to supersonics and maybe even eventually hypersonic speeds, to shrink the globe even more, to bring the globe together even more. There are high hurdles to do that in a sustainable way. At NASA, currently we are working on the sonic boom signature, trying to get the noise that is created by supersonic aircraft down to acceptable levels so that they can be flown over land. But there are certainly a lot of other hurdles in terms of efficiency of operation, landing and takeoff noise, emissions in the upper atmosphere, and so forth. In the bottom right is advanced air mobility, and that's really a revolutionary development that started with the application of UAS, the development of unmanned aircraft systems, and are now moving into passenger carrying eVTOL type configurations. And the promise is to deliver local mobility, add a third dimension to our transportation systems in cities, in suburban, in rural areas, and create new opportunity to move people and goods efficiently around our ever more congested cities. And in the upper right, all of these things have to fly in an airspace safely and certainly as efficiently as possible. And therefore we want to make sure that all of these vehicles can fly along their optimal trajectories and achieve their business cases, but doing that in a way that allows all of them to operate simultaneously and at scale. So that's a very challenging capability. But taken together, these 4 transformations can bring those societal benefits I was talking about: sustainability, greater mobility, and economic growth. So let's talk about the context for sustainable aviation. Of course, the International Civil Aviation Organization is where standards and goals and systems are harmonized for global use, and certainly that's the case for environmental impact and environmental standards. And the most recent is the release of the ICAO adopted carbon reduction goals. But what's notable about this is that the goals that have currently been adopted by ICAO, which is carbon neutral growth through from 2020, are not as aggressive as what the global aviation industry is striving for, which is a 50% reduction in carbon emissions by 2050 and ultimately net zero emissions. And I think what we'll find over time is that as industry pushes towards these more aggressive goals, and as our research organizations enable industry to push towards those aggressive goals, then ICAO will continue to adopt, to study, analyze, and adopt these more aggressive goals as well. And certainly ICAO is working at just that right now. They're working on assessing these more aggressive industry goals, and will likely, or we certainly hope that they will adopt these goals in future resolutions. Within the U.S. and certainly within NASA, what we've done is taken a perspective on what can we do for the next generation, and then what can we do beyond the next generation. And let's bring the combined research talents and capabilities of NASA, and within the U.S. FAA, industry, academia, and so forth, around common goals that can bring us together to deliver technology at high TRL that will enable industry to make decisions on next generation transports. And so the kinds of things we're looking at within what we're calling the Sustainable Flight National Partnership are advanced engine efficiency and emission reduction technologies, including going to a hybrid electric system. We want to advance airframe efficiency, and here you can sort of see a top-level iconic picture of the transonic truss brace wing, which is one concept that could provide greater airframe efficiency. We want to enable integrated trajectory optimization. It's one thing to have a very efficient aircraft, both airframe and engine, but we want to make sure that that system is flown as efficiently as possible along the most efficient trajectories possible. And also to be able to make sure that we're bringing into account things like potentially contrails and other things. How do we both minimize carbon emissions, but also do things like minimize contrail formation? And of course, we want to be able to enable use of 100% sustainable aviation fuels going forward. So ultimately, the kind of goals we're looking at for these next generation technologies, bringing those to TRL 6 in the next several years, is to get to enabling a 25 to 30% energy efficiency improvement for that next generation vehicle. In order to be successful, that needs to be done in a partnership, and it needs to bring together all of the key players. And so what we're looking at, again, for a Sustainable Flight National Partnership, is working together with the Federal Aviation Administration, with the Department of Energy, industry, and academia, everybody bringing their talents together, their capabilities in strategic partnerships that will enable the most critical technologies, the most impactful technologies, bring those to TRL 6, bring those to flight where needed. So we are planning on doing some very large-scale flight demonstrations, do large-scale ground demonstrations in key facilities where that's the appropriate way to go, and do that in a synchronized way so that by around the mid-20s or so, we could have a full suite of technologies, including, like I said, hybrid electric, advanced turbine engine technologies, advanced airframe technologies, and so forth. Bring them all together around the same time so that it provides industry the best opportunity to make decisions to bring the most efficient next generation transport to the table. Beyond next generation, we need to look at what is it going to take to enable aviation to essentially do net zero emissions and net zero impact to the environment, which is the real goal. Now that's a very bold goal, to have net zero impact, but I think it points us in the direction we need to go. And even while we're working on those next generation technologies that will bring substantial efficiency improvements, greater use of sustainable aviation fuels, and so forth, we can be working at low TRL, looking at those fundamental breakthroughs that can actually deliver net zero impacts. And the only way to do that, again, is through partnership between government, industry, and especially in this case, universities, really unleashing the potential of universities to innovate and to train the next generation of engineers, scientists and engineers that will actually then come out into government labs and industry and so forth and actually develop these technologies to higher TRL and develop them into products that we can see realized before mid-century. So a couple of examples on the page here. One is work we've been doing within NASA on distributed propulsion concept, using a hybrid wing body, airframe, And together, and behind that distributed electric propulsion concept is a turboelectric system that allows the electric motors, driving fans in a distributed way across the trailing edge of that vehicle. And so it's a superconducting electric drivetrain, most likely utilizing cryogenic fuels and so forth, and delivering a 70% reduction in energy use. Likewise, through our university leadership initiative, which we are increasing our funding in the university leadership explicitly to addrss net zero aviation. We've already awarded one net zero aviation award to the University of Illinois Urbana-Champaign, and they're developing a fully electric concept, again, a hybrid hydrogen fuel cell, superconducting electric drivetrain, and ultimately net zero carbon emissions. And so we plan on expanding this kind of work both internally and externally in order, again, at lower TL for now, in order to look at what the best concepts are, what those best technologies are, hopefully some real breakthroughs that will then give us the basis upon which to go to higher TRL, perhaps in the 2030s, again, aiming for being able to realize these kind of technologies in operation before mid-century. I thank you all for your participation in our IFAR panel today, and I really appreciate the opportunity to brief you today on NASA's perspectives on this subject. Thank you so much.
Following my colleague's earlier presentation, this will be part 6, or the last part of the lecture that focused on the technology roadmap towards zero-E. Hi, my name is Ibrahim Yimer, and I'm the Director General of the Aerospace Research Center at the National Research Council of Canada. By way of a quick outline, I'll start off with the decarbonization roadmap, followed by where we're today and where we're heading in the journey towards zero-E, and then try to conclude with some specific roadmaps. So I'm sure you've heard many times already that if no action is taken, the current contribution of aviation to global warming is projected to grow from towards 10 to 25% by 2050. So the question is, how do we get there in achieving these ambitious targets of net zero by 2050? I borrowed here a chart from the decarbonization roadmap for European aviation titled EU Destination 2050 to illustrate an approach that I found to be consistent across all the roadmaps that I've seen. So although improvements can be made through better operations infrastructure and incremental technology improvements, it's now known that the largest emission reduction is through the use of sustainable aviation fuels. That's shown here at 34% from reference emissions. And that's followed by the use of clean energy sources like electrification or hydrogen at 20% and development of new aircraft concepts at 17%. Now, we all know that SAF is important, and the industry has done a great job, a remarkable job actually, in defining what the drop in fuel should look like, and is really ready to implement it when the supply becomes available. So the focus of this talk will be on how do we achieve the target of 17%, integrating cleaner energy sources with new aircraft concepts or existing aircraft. So now let's look at what it would take to realize an electric or hydrogen-powered aircraft of the future. I would say both the challenges and the benefits scale up with aircraft size. Today, we are primarily at the kilowatt scale of the propulsion system size, and we should see commercialization of aircraft in the general aviation, commuter class, and UAM segments in the very near term. In fact, according to some sources, there are over 200 electric aircraft under development right now, some by traditional market players, and others are completely new entrants into the market. Due to the smaller size and range, this sector could most likely use any of the available clean energy sources such as batteries, hydrogen, or SAF. However, it makes up only about 1% of the total GHG emissions from aviation. Now, as we move to the larger regional jet size, we'll most likely need some degree of hybridization, where batteries can be combined with hydrogen or SAF. There are only about 5 demo aircraft programs that we know of that are under development today, that will most likely serve as a major proving ground for novel propulsion technologies before we see any scale up to large aircraft sizes. And as we get to the short-medium range aircraft, we've seen only 2 companies that have publicly announced plans to develop a new aircraft technology. Of course, the Airbus with their Zero-E that you all know, and the Wright Electric with the proposed all-electric aircraft. At this segment, batteries are most likely no longer a suitable option, and we will see either a hydrogen or SAF-fueled aircraft. This segment is also the largest contributor to aviation's GHG emissions at 43%, and will be really a key sector to make the technological advances in order to meet the overall Zero-E target. Finally, with the large wide-body segment, we will likely see a scaling up of the technologies that are developed for the short-medium range, and at this stage, we've seen only paper studies conducted. Now, among the many demonstration projects on the lower end of the spectrum, what I've shown here are just a few examples over the past 2-3 years. You see at the bottom a Diamond aircraft with serial hybrid electric back in 2018, followed by Harbor Air all-electric Dash 2 float plane in 2019, and Ampere Cessna 337 with a hybrid engine in 2020, and much more recently, about a year ago, Zero Aviation, an all-electric hydrogen fuel cell powered Piper aircraft. So what are the lessons learned and remaining challenges in this specific category of demonstrators? From a technology performance standpoint, we do see generally a great increase in the overall propulsion system efficiency and the cost to operate. However, key metrics like passengers, payload, and range are all lower than an internal combustion powered aircraft. We still need battery energy density to significantly improve in order to compete with the performance of an IC engine powered aircraft. I would say the same is true for a need to improve hydrogen storage efficiency. The other lessons learned, and Rolf has touched on it earlier, is on the installation of battery packs or H2 storage, which is really not standard across the various demos we've seen today. Each has its own merits and challenges, and we may need to eventually see some convergence of this from a safety and regulatory perspective. Safety of high voltage systems and batteries has been one of the biggest challenges as well, and there is a lot of lessons learned on this aspect of safely integrating the batteries with the aircraft systems. We have also learned that there is a need for a means of compliance or certification in order to maintain the stellar safety record of our industry. This is being developed concurrently through standard groups like ASTM, SCAE, and EuroCAE, and will need to be globally harmonized. So where are we heading next? Several regional jet aircraft demonstrators have been announced that hopefully will take to the sky in the next 3 to 5 years. We will likely see and learn more on how to operate and certify a hybrid system for this class of aircraft, which will be paving the way for a certified conversion kit of some sort for regional aircrafts. Now, here are some examples in the immediate horizon. And again, we see some differences in the configurations. On the top, you see the image of DLR and MTU proposed hybrid electric donate by replacing the engine on one side with a 0.5 megawatt electric motor that may be battery or fuel cell powered. In the middle, you will see Pratt & Whitney Canada and de Havilland Canada are replacing one engine of a Dash 8 with a hybrid configuration that has a gas turbine combined with an electric motor. And at the bottom, Universal Hydrogen and its partners are proposing an all-electric hydrogen fuel cell power aircraft with a 2 megawatt propulsion systems. Therefore, although these are small in numbers, these demonstration programs will provide significant learning and the big step towards Zero-E in the near future. But before we get there, or in order to get there and further scale up to larger aircraft, here are some of the technologies that are needed. Just to touch on a few of these. Battery pack energy density is currently today around 170 watt-hour per kilogram. And some studies suggest that we need to get above 700 watt-hour per kilogram for large aircraft application. Today, electric motors for aviation have been demonstrated up to 2.5 megawatt with a power density of about 5 kilowatt per kilogram, but we still need motors with sparks greater than 5 megawatt and a power density of about 13 kilowatt per kilogram. And for implementation of hydrogen, one of the largest barriers to overcome on board the aircraft is the weight penalty of the tank. A useful metric, perhaps, is the hydrogen tank storage efficiency, which is really basically a measure of how heavy the tank is compared to how much fuel it holds. Currently, the state of the art is around 14.5%, but studies have shown that we need to improve to above 35% for large aircraft applications. Now, besides the technical challenges, of course, there are other challenges in moving towards electric or hydrogen aircraft that are not just aircraft related. For example, large amounts of electrical energy will be required for charging batteries or producing SAF or producing hydrogen. As well, new airport infrastructure will also be needed. For example, a recent study showed that replacing the jet fuel at Montreal Airport alone will need the equivalent of about 11 terawatt-hour of energy and 220 kiloton of hydrogen. So we will really need to have a multi-sectoral approach with all stakeholders involved, from the fuel and electricity producers to airport to regulators and to OEMs and others. And now to conclude with some comments on published roadmaps. We've seen the development of several zero-E roadmaps towards achieving the aviation emission targets I mentioned at the top of this presentation. While there is really a shared goal and target to be achieved, they have different levels of commitment and timelines. Obviously, it's difficult to provide a comprehensive summary and a comparative analysis here on a short presentation like this one. But I would just say that they range from roadmaps by individual airports and air carriers, for example, American Airlines, to industry associations and organizations such as IATA and ICAO. EU, European Union, seems to be leading the way and have put out some very good examples. Worth mentioning are Destination 2050, which I mentioned earlier, by NLR and its partners, and a Path to Net Zero by Sustainable Aviation in the UK. Two documents that I recommend reading if you haven't already done so. Now, having said all of this, I believe international forums such as ICAS-IFAR and ICAO should continue to contribute towards the development of a global framework, much like CORSIA, in order to make it easier to engage broader stakeholder groups outside of the aviation industry, such as fuel producers, and achieve aviation emissions targets globally with collective effort. And I thank you very much for your attention.